uh, infuses the thought process to look for new things, at least in the domain of research, which people can use at least in their future research as well. So to begin with, let me share my slides so that it will be a better way of communication. And like the title that was suggested, it includes very basic theme. And let me just go through the slideshow and see that if we are able to. Can you see the change in the slides? Hello?
I think it is fine.
So slides are changing.
No, sir.
No.
Actually, instead of sharing one tab, you are sorry. I request to share the whole entire window or entire screen.
Yeah, it works sometimes in this. We have a problem.
Now it works, sir. Now it works.
No, it is working now because now I am not in the presentation mode. It is like I am in a it's working mode. So let me maximize the window as well. So this is the maximum that I can do. So in this case, it should work, right?
Yes, sir.
Okay. So in presentation mode, there are some issues. So I don't know why. Usually it happens. I believe it is visible to all.
Yes, sir. It is perfectly visible.
Okay, fine. So let us take this very simple tool. Like everyone knows what is light, right? And we want to use this as a tool to understand the materials properties and important materials properties, for example. Very simple fundamental aspects of interaction of light with matter that leads to the very intrinsic properties of materials. That will be our objective. If at the end of this whole series, whole discussion, we can come to a conclusion that, okay, many of you might be using some of these tools, but maybe not getting to use this as a full potential. So after this lecture, my intention, my job will be, means I will be very happy if the take-home message is given, that use it to the maximum extent to extract the best information that you can. A very simple tool that can give you enough information to find out the intrinsic materials properties, which probably are unknown in the beginning, are probably known. You want to re-verify them as well. This is the intention of this particular discussion as well. So fine. So what we will try to understand, we will try what phenomena will occur when the light is shined on a material. Very simple thing, right? We all use this, like for example, a simple mirror that we are using in everyday life, right? How they are made, that is a question to understand. What determines the characteristic colors of material? Many of us are using, believe in astro, so we believe gems as well, right? So you see multiple color gems are available, right? So we can see that what is the basic intrinsic reason that leads to different colors to those gemstones as well. What are some materials? Why some materials are transparent, other are translucent or opaque? That is the question, right? How the properties will change when a material changes its geometry. If time permits that, we will aspects into this case. For example, when I say that when a material changes its properties, when I change the geometry, for example, if I take a bulk material and I say bulk material means its dimensions are in micrometer or even larger, right? That is the difference. But if I reduce the geometry from taking this material from microscopic dimensions to the nanoscopic dimensions, how the things will change is our intention as well. Right? So in time permits that we will end up here as well. And some of the applications that we will see, very easy applications that we will use in chemistry as well. A very simple, straightforward technique to use very important information they can extract, and indirectly even they can predict the size of quantum dots or nanoparticles as well. So to begin with, what is the spectroscopy that we need to understand? Like a spectroscopy measuring the physical property as a function of incident energy of frequency. And what is the incident energy or frequency available is the whole electromagnetic spectrum that is available to you. So you have whole electromagnetic spectrum available to you. People use different energy range and they call at a different spectroscopy, right? People use microwave, they call microwave spectroscopy. People use infrared, they call infrared spectroscopy. People use UV visible, they call UV visible spectroscopy. People use X-ray, X-ray spectroscopy. People use gamma ray, they call it gamma ray spectroscopy, or even mass bar is some name is given as well. And radio wave spectroscopy as well, right? This whole electromagnetic spectrum is available to you. You find out the source, you select the reason, and you how that particular section of your electromagnetic spectrum to interact with your material and then enjoy the outcome of that interaction. That is the spectroscopy. So spectroscopy is measuring physical properties as a function of incident energy or frequency selected from the whole entire electromagnetic spectrum the way you like. Where your source is available, you select that particular point and then distribute it. So a spectrum, whenever you do a spectroscopy, you are always going to collect a spectrum, right? So a spectrum is nothing but on x-axis you are changing your incident light frequency or energy. So you change your energy. So you can say I can plot on the x-axis energy and y-axis what you collect. You collect the number of photons coming out after interaction from the material. So that is very important thing that we collect it. Right? So on the y-axis we collect the number of photons collected per unit area of your detector and per unit time that you call incident. Intensity. Right? So that is there. So that we need to plot as a function of energy. And y-axis is always same. It is collected number of photons per unit area per unit time. Where x-axis you are free to write very different names. Right? For example, some of your name is, for example, I can see Sanjay Sharma. This is written name, right? Then he has many different names as well, which always imply with the Sanjay Sharma. At home, his parents may be calling with a different name, right? His friends may be giving Sanjeev another name, right? So he may have all different names, all of them converge to the same meaning, Sanjay Sharma, right? So we use synonyms, right? Depending upon our choice, we can use the x-axis as different names. For example, energy is one of the names, wavelength is another name, wave number is another name, right? You are free. They are all synonyms representing the same thing, converting to the same point. But we have a mindset, right? Like friend Sanjay Sharma, friends like try to call Sanjay because they feel more comfortable, right? So spectroscopists work with a different type of spectroscopy. They are familiar or they are most convenient with working style of certain things, right? So if you see, sometimes the same spectrum is written in the terms of wavelength, fine. In terms of energy, fine. In terms of wave number, fine, right? The x-axis can use these synonyms depending upon the use and depending upon the flavor of the person or taste of the person, what he likes to see in the information, right? That is there. So now those became convention, nothing like that, those are hard to pass through and always convert energy into wavelength or into wave number. But now those are conventions, we follow those conventions as well, right? So I will not looking into those aspects, but very easy to convert them, right? So optical spectroscopy, where we are focusing on today, it's like the optical part of the electromagnetic spectrum. We will include only visible to UV. We exclude IR, we exclude the higher energy part as well, right? So we are working in the region which we can visualize from our eyes as well. That is the part, right? Some part maybe IR, you can cover it. This light can be focused and controlled by mirrors, lenses, and optical diffraction gratings, and that's why easy to work, right? So visible light, like I said, light is in the range of 400 nanometer to 700 nanometer. If you collect to the UV, sometimes you have a source that works from 300 nanometer to 800 nanometer and so on, right? And the energy is like 3.1 electron volt, 1.7 correspond to 400 nanometer to 700 nanometer, right? You can use the relation, convert them to respective form from wavelength. Very similar relation, very simple relation is equal to Hc by 10. Right, all of you know this, right? So fine, we define UV greater than 3 electron volt, IR less than 1.7 electron volt. So these are not very sharp boundaries, right? So these are boundaries which are very diffuse boundaries. So you can plus minus error bars, that doesn't matter, right? Then I said sometimes you also express wave number. Wave number is nothing but, right, 1 over lambda. Means how many lambdas are available in 1. If I express in centimeter, so my centimeter, 1 centimeter, how many lambdas are available, that is the wave number corresponding to that. A usual convention is you can write in meter inverse, you can write in millimeter inverse. That doesn't make any change in the actual sense, but that will change the numbers, right? So 1 over lambda, usual convention is right in the centimeter. In 1 centimeter, how many waves are right? So 1 over lambda is right in centimeter inverse, right? Number of waves per unit length, typically expressed in centimeter inverse, it means how many waves are available in 1 centimeter, right? So that is, for example, corresponding wavelength, I have 700 nanometer. If I want to compute the corresponding wave number, it turns out to be 14,000 centimeter inverse, right? This is also related to the wave vector, right? 4 pi lambda. Very simple, right? So now we have a very basic flavor of what is a spectrum, right? What kind of source that we are going to use. We are limited to optical spectroscopy, that itself will give you plenty of information. Then we know what is the outcomes, how it should look like. Outcome will look like on the x-axis you have energy or wavelength or wave number, and on the y-axis, after interacting with your material, how the light you are collecting, how the light is getting changed from the incident light, which you have intensity, for example, I naught, and how the interacted light signal is changing, that we need to collect, right? Now question is, how many types of interactions are possible within a material? That is right. So you find, I have an incident light, how many phenomena can happen? Very simple. It can reflect. It can propagate through sample, and during propagation, many things can happen. It can get absorbed. It can get transmitted. Here also, if absorption is happening simultaneously, emission can happen, that can also emit the light signatures as well, right? So various phenomena can happen. Now, where you put detector on this side, where you put detector on this side, where you put detector to detect it, depending upon the detector and your sample interactions, you decide and you call the respective spectrum corresponding. This is my transmission spectra, this is my reflection spectra, or this is my emission spectra, or this is my absorption spectra, right? So simple name, right? Nothing like is great here. But we simply give a thought process that how the light can interact, how the incident light can interact, and the interaction mode you can opt, and that interaction mode will define the respective spectra. And that's of our interest. And that's where we will see. Here, we will try to understand how more physically that is happening, right? All of us will try to understand how these signals are generated in a material and how the different material will respond to these signals differently. Right. So this is like whatever we have. We have an incident light. Let us give a more thought on the propagation side. If the light is propagating in a medium, then various phenomena, optical phenomena can happen. One is light is getting refracted, right? Refracted, if light is getting refracted in the medium, we get a refracted index, and as you the velocity of light in the vacuum divided by the velocity of light in the medium, right? Very simple. It's not so that we have. Another thing is that absorption can happen. Absorption can happen a normal absorption, or you can have resonance absorption. That is also that, right? Luminescence, okay, light is getting absorbed, and then you get a spontaneous emission from your material as well. So in case of absorption, light is getting diminished, your intensity of light will be decreased, right? Whereas in case of emissions, you will get a different wavelength light. That is, it's not like the same wavelength that I'm getting. In case of reflection, light is of the same wavelength. In case of transmission, light is of the same wavelength. In case of emission, the incident energy may be higher, and the emitted signal may have a lower energy as well, right? Scattering, both possibilities are there. You may have elastic scattering as well as inelastic scattering, right? Inelastic scattering will also give you wonderful new dimension in the optical domain, which we call nonlinear optics, right? That we can use, we can find out here, right? A new way of looking the materials as well, right? Very simple, like all of us know how the absorption takes place as the light passes through a sample, right? Very simple. In the same case, when the light is passing through a sample, very simple looking at this ray diagram, is getting absorbed, right? When the light passes through a sample, the intensity of light decreases. The absorption will depend strongly on the wavelength of the light. Not all the wavelengths, not all the energy of the incident wave will get absorbed. Only certain things, certain waves will be getting absorbed, right? That is there. Certain intensities may be reduced. That is there. The intensity measured in units of power per area. That is, like I already said, it is intensity, number of photons per unit area per unit time. That we call intensity. Time. H is for one wavelength. If I have a wavelength varying, sorry, wave frequency varying from nu 1 to 2, then I need to integrate. Then in that case, this is di, right? Then I need to integrate I which will equal to n. It's also a function of nu, n nu, h nu, d nu, where n nu is a distribution of the electrons, of these photons. So I need to find out the density of distribution, density of these photons, how they are distributed, photons in their energy distribution. And then I can integrate, and then I can get the total intensity as well, right? And you know what is n, right? These are like photons, right? They follow certain statistics, and then you know that what statistics I need to use, right? You know, Planck's statistics, right? Planck's statistics you use and integrate, and you will get the total intensity. But keeping that as an aside, looking into a classical way of looking at things, the relative change in intensity is proportional to the distance traveled through the material. That is, like, if the distance traveled by the incident light is x, then change will be proportional to that, and will carry a minus sign y, because as we move from point x1 to x2, x2 minus x1 is positive, but I2 minus I1, intensity at the second point has dropped with respect to the incident intensity. So I2 minus I1 will become negative. So that's why this minus sign is coming, right? So I2 minus I1, because of the change is on the lower side from the incident intensity, that's why negative sign will carry, right? So delta I over I is proportional to delta x, and that proportionality is taken care by this alpha. That is a constant. That particular wavelength, this is a constant. It means alpha is also a function of lambda. It is not independent. It's not, we define alpha, right, in general, but it is a very complex function of wavelength or incident energy or incident wavelength that has a dependency. That's where you, whenever you plot the absorption spectrum, you see it's not a constant, right? You will find that alpha is also changing with the incident energy as well. That's why, right? So di over dx, you can hear it, and you can simply get a very simple that you are already aware of. I is equal to I naught, okay, sorry, you see, e to the power minus alpha x. Right. So very simple that we get. The absorption coefficient, what it does, it tells you whether the intensity will fall very slow or very fast, depending upon the material's relation with respect to the incident light. Right? This is a function of frequency or wavelength and is a characteristic of a particular material. So this can be used to distinguish between the different type of materials, like example that we will see, whether it is a metal, whether it is an insulator, whether it is a semiconductor, or whether it is a semiconductor with a lot of carriers in that as well, right? So we can use a very simple parameter, that is the absorption coefficient. We can put it as a function of energy or wavelength or wave number, and then we can characterize the material. We can try to find out, distinguish the nature of it in which it will fit. Right, that is also our objective, right? Okay, how from where we get these reflected signals or transmitted signals or absorption, right? So very simple, right? All of us know the Maxwell equations from where we can start. So because electromagnetic wave is going to interact with your material, so you know the incident wave, right? We can write very simple. All of you can open the Griffith electrodynamics, and then you see the Maxwell equations, interaction with the material just after vacuum from free space to the medium interaction. You will find the reflection coefficient, transmission coefficient, and so on. The same thing we will do, right? So we have a coefficient of reflectivity that we define as reflected power or incident power. Transmission or transmittivity is the transmitted power and incident power. And if your material is transparent, it doesn't absorb anything, R plus T is equal to 1. Which is not going to be the case, because I have always some absorption. So ideal relation is R plus T plus alpha is R. You can call capital A, right, with respect to this reflectivity, transmittivity, and absorptivity, capital A, R plus T plus capital A is equal to 1, right? You can also define the refractive index corresponding to your material, because you know that as light will propagate, the velocity of light will change, and then refraction will also happen, right? The refractive index can be defined. Absorption coefficient, like we have already defined with this particular, right? If I integrate with respect, I define T is equal to 1 minus R, and I take into account the I part. Then if I take T, I want to find out what is the intensity of transmitted light at this particular plane. This is my medium 1, this is my medium 2, right? So at T here, it will be 1 minus R times the loss in absorption, that is e to the power minus I alpha. If distance is, travel distance is L, that is L. Then if this distance is also L, that is like after this, it will be reduced by 1 minus R2. So it is like, if I assume both reflections are same, qualitatively this is 1 minus 4 square, R square, it will be 1 minus alpha. Like I said, this is not our target, but just like I have said in the beginning, this is also one of the phenomena that takes place by interaction. In this case, the incident frequency should be more, right? So you have a higher frequency that gets absorbed, hits the ground state or valence band to some excited state electrons, and then it will relax, come to a state, and then it emit, right? So in that case, the emission is less than, emission energy is less than the excited energy, and will not do this more. Only just I will say it is proportional. If I take into account scattering, then I naught e to the power minus n sigma s times g, where n is the number of scattering centers and sigma is the scattering cross section. And if we work more detail, like scattering, Rayleigh's scattering is proportional to 1 over lambda to the power 4, coming from again this expression that we can work it out. But I will skip here because again that is not a part of our intensive discussion. We will be focusing on optical constants, optical coefficients, and try to find out the important materials properties of our interest, right? Right. So I have incident wave light, like I said that okay, I have an incident wave like E is equal to E naught e to the power I k z minus omega t propagating along the G axis, right? Then refractive index, like we have defined, we can come up with the again same equation that we have. Refractive index is not a simple quantity. It is sum of complex and real part n plus I k, right? That we know. If I use that, then I can define the extension coefficient like 2 pi by lambda times n. If we work it out, extension coefficient turns out to be n plus I k times I times k. This is a wave is equal to refractive index n plus I k times omega over c, where omega is the energy of your incident wave. Substituting back, you know that incident wave is equal to E naught to the power I k z, and you also know after introducing this k like as a wave propagator, in this case, then your EZT signal is like e to the power I omega n z for c minus omega t. I substitute this particular part, I take out real part and imaginary part. So when I did E0 is minus k omega over omega times t over c, it's like real component that will take it out. Means k is still extension coefficient, but this I and this I makes it a real component. Whereas n it still goes with this I, so that will part will be the complex of exponential of complex factors, right? Now, if I take this I intensity, this is that okay, this is my energy, how this is changing, means electric field component, then intensity will be again mod of E times mod of E square, which is like E to E star. If I play with these numbers, I will end up with n, which is equal to square root of epsilon r, where epsilon r is the refractive index of your material, and then that is also coming up with the two components. One is a real component, epsilon 1, you can say, and one is the imaginary component, epsilon 2. Right? When you do a square, then it is like epsilon r. That is. So this this comes with a simple manipulation of incident light, allowing to interact with the material and then working out the intensity signature and relooking the refractive index in terms of the materials properties. So where I have used the materials properties, how the light will start interacting, will interact with respect to refractive index or with respect to the dielectric constant. So this is how we introduce the interaction of incident light with the material. So these are the components where the interaction of light, incident light, will take place and will depend upon these numbers of the material. And these numbers will depend upon the type of material that will use. Right. Again, I work it out. Suppose to somehow you can manipulate to know what is epsilon 1 and epsilon 2, you can find out n and k because of these relations. Epsilon 1 is equal to n square minus k square and epsilon 2 is equal to twice n. Right? Or vice versa, if you can measure n and k, means n is refractive index and k is extinction coefficient. If you can measure them, then I can work it out to get epsilon 1 and epsilon 2. Like these are coupled relations. So anyway, that experiment you perform, and somehow you are capable of knowing n and k, then you can know epsilon 1 and epsilon 2. Or if you are able to measure epsilon 1 and epsilon 2, you can figure out n and k. Right. Theoreticians work to get epsilon 1 and epsilon 2. So for example, if I want to find out the material's properties, right, how this will respond to the incident light, I will try to find out my dielectric constant as a function of energy. Then what I can do, I can revert back this epsilon 1 and epsilon 2, which is real imaginary part, and I back into the equation and solve them. I will get n. Experimentally, it's relatively easier to find out the extinction coefficient as a function of energy and wavelength. Then I can work it out to get epsilon 1 and epsilon 2 from the measured quantities that is there. So the interrelation between these two quantities are like this. Any one of them is fine. Right. So again, these are not independent, they are variable and will depend upon the wavelength or energy, whatever you call. Now you can define constants on it. My system is not very absorbing like it is weakly absorbing medium. Then extinction coefficient will be small. When extinction coefficient is small, then you can try to get rid of k, because k is small, because n is 1 over square root of 2, that whatever you have, epsilon 1 plus epsilon 1 square times epsilon 1 to the power half. So epsilon 2 is, since k is small, epsilon 2 is going to be small, so you can exclude that. So I have epsilon 1 plus epsilon 1, that is 2 epsilon 1, then it will be square root of, again square root of half, then square root of 2 epsilon 1. You cancel square root 2 and will be square root of epsilon. That depends upon if this is the case. Then another thing that is much easier to work it out, other than in a more generic nature, you work with a normal reflective, normal incidence condition, right? Again, this is fine. If I take light incident falling onto your sample or material at 90 degree, then in that case, it is relatively easier, and the reflectance or reflectivity works out to be n minus 1 or n plus 1 whole square, complex. In more simple form, n minus 1 whole square or n plus 1 square, k square or k square. That is right. Very simple. So now this relation is known to you, and one of the quantities that you can measure. You cannot measure directly k, you cannot measure directly n, but you can measure r as a function of it. So now I have r, reflectivity, as a function of wavelength. I do measurement, right? Like I said at the beginning, that you have 3 signals with you. So you have a reflected signal, you have with respect to your incident signal. So you can measure what fraction of light is getting reflected. Right? I can measure capital R. And now I know the relation between R and N and K. Right? So typically those who have done some fitting, they know this is the relation. What they can do, they can try to fit with different N and K as a function of lambda, and then try to see that when the value of N and K for those wavelengths will satisfy this null R, and you can back it and then get it. right? So from this only reflectance, normal reflectance also, you can try to get N and K, but little more mathematics is involved. You need to do the nonlinear fittings because these are not simple equations, but yes, doable. You can use any programming skill that you are aware of, like MATLAB or Scilab, very easy to work with them. And simply you take reflectance data and fiddle with n some functional form. You take it to generate the values and then rechange simultaneously because it will be a self-consistent. You need to find out computed R for a given n and k and R decay difference. If the difference is less than 1%, you say my data is matched, and you can get variation in n and variation in k. But little tricky, right? Because it's nonlinear fitting, you need to spend some time so that your solution is not diverse. But a simple measurement that where you measure experimentally R as a function of energy will allow you to fiddle with n and k to get back for your energy. Right? This is how from experiment we can derive these quantities. That is like theoreticians prefer to work because we can work more independently with epsilon 1 and epsilon 2, and then we can generate n and k, and then we can match with the experiments, right? So when I can get epsilon 1 and epsilon 2 more intrinsically, right? I will calculate the material's properties from again starting with the very basic equation of material, that is again Schrodinger equations. We modify it as per our need depending upon the approximations available to us, and then we try to solve it, right? So up to this point, whatever we have, similarly we can define transmittance as well with respect to normal incidence, and then we can define transmittance as a function of n and k. So you can measure transmittivity as well, and with respect to the transmittivity, you can find out the n and k by fitting as that data. Otherwise, you have two data, r and k, and you can compute from one and you can test on another as well. So they are fitting or not fitting properly. Right. Now, up to this point, we have seen, okay, light is coming from outside, interacting with your material, and then we get some information in terms of reflected signal, or vice versa, you can say in terms of transmitted signal, and then try to correlate with the material's properties, which are n and k. Right. That is clear. But what is happening at the macroscopic level is again important, right? This is like a macroscopic, like everything looking by eyes, collecting the data, and then see that how the things are changing as a function of energy. Now, what is happening at atomic level, that why this absorption is happening, why this reflection is happening, we want to understand that, and then we can see very simply, right? Again, like with a very simple atomistic view of these processes. So whenever you have an atom, right, very simple. Let us go back. So far, we have collected the entire material, and we are looking like light is falling on your material, and you are collecting the signal that is reflected back or transmitted. Right. Now, let us look back. What will happen when you have an atom and then light is coming to it? When light was absent, your charge distribution is uniform. The center of mass of your positive charge and center of mass of your negative charge in an atom coincide with each other. So you will see like, okay, no charge buildup is right? Classically, we consider an atom to be a positive nucleus surrounded by a negatively charged electrons. When there is no light or no electric field, since both the centers of your positive and negative charges coincide, so there is no charge separation, so no electric dipole. Now you switch on the electric field, right? You switch on the incident electric field, right? What will happen? That's if electric field is permanent, then what will happen? The positive charge will displace and negative charge will displace opposite to each other. Right? So in that case, there is a permanent displacement of overall positive charge. So the center of positive charge, the center of negative charge, they are separated with respect to each other. Now, but their charge amount is same. So in that case, you build up electric dipole. So remember, light is comprised of alternating electric and magnetic waves. Magnetic waves you leave aside, the positive nucleus and the negative electrons move in opposite direction. This produces an electric dipole. That's what we have discussed. at the center of positive charge and the center of negative charge no longer coincide, then leading to a local electric polarization. So this is like when we have a fixed electric field. Now, what will happen when we have an oscillating electric field like electromagnetic field, right? We are changing, electric field is switching plus minus, right? So what will happen to this dipole? This dipole will also try to follow the applied field, right? Switching of your electric field will try to switch the direction of this electric dipole because of the relative displacement of your positive and negative charge, right? So your disk will also oscillate, right? When it oscillates, then my problem becomes easier, right? Why it becomes easier? Then you can apply a simple harmonic equation, right? So if charges are displacing, then you can write a simple force equation, right? Mx double dot is equal to minus kx, right? But kx is the force, right? F is equal to m into a. But in this case, actually that is applicable. But we have beyond that. What is beyond that? The system will also experience damping because it is inside the medium as well. Right. So in that case, I have a force which is oscillating force minus charge q times E, right? So minus charge times E minus E, q times E is minus E times E0 for I omega t. I have x double dot, that is the acceleration of my nuclei, plus I have damping force. Damping force is nothing but proportional to velocity, right? So gamma is my damping constant time. Usually you have experience with the minus gamma, then I will keep towards the force side. Then I write it as F minus gamma times mx. That's why I brought it in this side. Plus, since we have a positive and negative charges, so they will interact with each other, right? So Coulombic interaction will be there as well, right? So that is like ZT square times the displacement x, right? Where it is, right? This is potential energy V into x, right? Because we are experiencing the force. So 1 over 4 pi epsilon naught Z square by r cube times the displacement. And this is force. So we modeled our problem of oscillating electric field, induced oscillating electric dipole moment, and this oscillating electric dipole moment we model with respect to the forced harmonic oscillator. Why forced? Because this is still happening. The left hand side will be still true even if you apply an phi, but you are applying continuously. This is continuously interacting. The force is always applied. So you have a forced harmonic oscillator, right? I have forced oscillator because force is continuously applied on the system, on the atomic system. So this is my atomistic view of looking the interaction of light with my system, right? How the atom is responding with the applied electron. So this is my, and if this is the case, right, you can take the help of mathematicians. You can even try to solve it by yourself, right? So this is the second order differential equation, which is non-homogeneous, right? So what I need to do, I need to first find out the solution of my homogeneous differential equation. Then I need to find out the particular differential equation with respect to this, skipping those mathematics, assuming that you can take the help of any mathematical space. So you can solve this particular equation, right? Whenever you read partial differential equation, this is one of the things that you do. Then, assuming that you have done that exercise, we end up with the final solution. Then we find a relation between the displacement, because my solution will be the form of x. Right? So this is my solution. X is equal to minus charge q, what is in this case is minus E, times electric field E divided by m times omega naught square minus omega square plus I omega gamma. Right? This is the solution. And the other way is there. I take this particular as a solution. I compute x dot, x double dot, substitute x dot and x double dot, right? Because these are the function of omega. So I substitute this, I dx over d omega, right? Whatever here, dx over dt. Dx over dt, omega is a function of t as well. So I substitute back it, then I can get the solution. The right hand side will be same after substituting these things as well, right? In this case, when we did, we have also approximated this particular term is omega square. Right. So this is like mx double dot plus m gamma x dot plus omega square. omega naught square, like omega naught z square or 2 by epsilon naught r cube times x omega square. So now this is there. So now I have a solution. The displacement is now known to me. Now if I know the displacement because of the applied electric field, I can find out what is the dipole moment of my system, right? So dipole moment is just like q times displacement times d or q times l, whatever you have. This x I have found. This x I have computed. This is for individual atom, but your material is not made of a single atom, right? So you need to sum all those for all possible atoms present in your system. So that you can say, okay, average it out, like summing for all the atoms, I have n atoms, so n times x. Now you know this x, and then you substitute it here. Whatever we have x, this is that you can substitute it here. And you have already, then you have E over m omega naught square minus omega square I plus I omega. This is here. Right, that we substituted it here, and then this I can get total P. Now, with respect to the dielectric constant, if you recall your first chapter of your electrodynamics, means electrostatistics, then we define the polarization P is equal to epsilon minus 1 times epsilon naught E. And then I got this expression P is equal to NE square times E over this particular thing, this factor. I got, right, I can directly compare epsilon minus 1 epsilon naught is equal to rest of the factor. E will be cancelling. So I got a theoretical expression for dielectric constant epsilon, or you can say epsilon r, whatever you like, is equal to 1 plus, because this one will be coming, NE square. Rest of the things were there, epsilon naught is in product, will come into the denominator. So now I got the dielectric constant of my material by a very simple, using very simple approximation of oscillating atomic view in presence of external electric field inducing the dipole moments and summing all the dipole moments of the material. So I got my very simple dielectric constant relation in terms of the energy of omega. So epsilon is a function of omega or wavelength lambda. Now what is interesting that, okay, this is a complex quantity. That's what I have, again, I have used a priori as well. So here, I have not used the atomic view. I have tried to solve simplistic equation of electromagnetic waves to change and in change in electric field, computing the change in electric field components under reflection, under transmission, and then we computed this R and these other quantities. Here it is on pure atomistic view. Just we simply took that, okay, that the incident light is inducing electric dipole moment that leads to a very simple expression of dielectric constant of your material, and also explaining you that this is a complex quantity. And you know, if it is a complex quantity, you multiply by numerator and denominator with the complex conjugate, you can separate out the real and imaginary component. Do this little exercise, we separate out the real dielectric constant and the imaginary dielectric constant. And these are here in front of you. And remember, you have a relation between the real and imaginary dielectric constant for your n and k. So if I know epsilon real and epsilon imaginary, I can find out that is there. So this is also from a very simple approximation we started with, and then we know the omega naught, which is not known to be, that is like something that we still want to compute, that we will look into. And then omega you are changing, so you know this is your controlling factor. Epsilon 0 is known to you, n is known to you, m is known to you. Gamma is, again, you can say if you don't know, then you can use it to find it out what is the gamma. Or we can approximate with some parameter rather than taking this as a function of lambda as well. Okay. Then now I got my real and imaginary component, and I got the picture that why, if I have this real and imaginary component, then the imaginary component is something that is related to your extinction coefficient. And that is something related to your extinction coefficient that leads to the absorption in your system as well, that we will see. Right. So the complex refractive index N is defined as n square is equal to epsilon or n is equal to under root epsilon. This is also a complex number where you can write n is equal to n plus ik or n minus ik, where n is the conventional refractive index and k is the extinction coefficient. Now, fine. So if I recall, okay, that whatever the speed of light is, and in transparent material where the refractive index is n, the speed of light will reduce, right? It will be c by n. The wave vector corresponding wave vector is 2 pi by lambda. So lambda is nothing but nu over c. So with respect to the incident wave, you can say corresponding n if you introduce, then it will be like 2 pi n over lambda naught, where lambda naught is the wavelength corresponding wavelength, free space wavelength. That is there with respect to your material, right? So the respective wavelength has changed, and that changed wavelength is introduced. It's lambda naught by n, so n is going into the numerator. So now if I substitute this k in my electromagnetic wave expression, right, and this n I use, this is my refractive index. If I use this as a complex quantity, then I use it here. Right? Then I use the simple form n is equal to n minus ik, separate out the real component and the imaginary component. Then my wave becomes E is equal to E naught to the power I omega t minus kx, right? Where k is this one, this k, this is the extension coefficient, right? Times exponential e to the power minus twice pi k over lambda times x, right? So this is saying that if my electromagnetic wave is passing through a medium and travel a distance x from the incident point at x is equal to 0, you can say, then this amplitude is going to decay exponentially, right? The amplitude of electromagnetic wave, because this E will become E naught e to the power minus twice pi k over lambda times x. That is there, right? Rest is moving forward, right? Oscillating wave that you have from the beginning. So that is interesting. And if now I want to know intensity, then I is equal to mod of E, I is equal to mod of E square. So this will be exponential factor with the mod will become 1. So what will be left with E0 square, e to the power minus, it is a square, so 4 pi k by lambda times x. That's where I is equal to mod of I naught, E naught is square, e to the power minus 4 pi k over lambda x, right? Now, remember, we have started with the expression that as we move, then we have introduced di over I is proportional to the distance traveled x. So that was I got I is equal to I naught to the power minus alpha x. So that is a simple expression that is coming from the same thing from where we have started in this picture. And then I got the same expression I is equal to I naught, because E naught square is I naught, to the power minus alpha x. I compare them, alpha is nothing but 4 pi k over lambda. That is the right extension coefficient over lambda, or the complex part of the refractive index over lambda. So that is how you can compute the absorption coefficient as well. Or the other way, you can measure the absorption directly from your experiment as a function of lambda, and then I can use this relation, right? I measured alpha as a function of lambda, then I have this relation, I can find out the extension coefficient k for my problem. And I did k, then I solved here, which I said that it is a difficult task to fit, right? Where I said it here. I said it is a difficult task to fit it. So you do more than one experiment to complement, to ease your fitting part, right? So I said in the beginning that if I don't know anything, I need to put n as a function of lambda, k as a function of lambda. That is a little tricky job and more complex job. Usually you will end up with getting things diverging. But to avoid that particular thing, to complicacy, I did one more measurement. I measured the alpha. Then I computed k as a function of lambda. So I don't need to do fitting on k side. So only I need to do fitting on n side. So 50% complexity will be reduced. Whereas now it was like a 2 variable process. Now I got only 1 variable process. Much easier to work out mathematically or in terms of mathematically fitting this. So that is there. So I complement my reflection experiment with the absorption experiment. I reduce the complexity, and then I can get n as a function of lambda as well. Right. Looking into more detail, up to this point, we are collecting the information that we need and that we can use to couple the materials properties with the some signatures of interaction of incident. Like reflection, like we said, we took the normal incidence, again very simple case. We work with reflection coefficient to define again like a reflected signal divided by incident signal. So very simple thing. Again, I said those who are more interested to look into this aspect, please look any electrodynamics book, but I think Griffith is most common, that you can see that what will be the expression for R. And then capital R, which I said is the reflection, right, or reflectivity, that we can say is mod of R square or mod of ER over EI square, right? So for normal incidence, R is going as N1 minus N2 over N1 plus N2. It's very simple, where N1 is your medium and N2 is another medium through which reflection is taking, incident wave coming from N1 to N2. So N1, if I take air, then it is 1 minus N2, and N2 if I take 1 minus N over 1 plus N. Since it is a mod, so I take N minus 1 over N plus 1. That is it. Then I will say reflectance or reflection, reflectivity, it is like mod of R square, which is like intensity of R or intensity of incidence. Right? Then I substitute back it here, then I will get N minus 1 whole square plus K square over N plus 1 whole K square. That's what we have promised in the beginning. And these relations are known to you, that we compare N square is equal to N square minus twice INK minus K square, which is IK square. That gives you the relation that we have earlier as well. Now looking into the transmittance, again, transmission coefficient will be the ratio of electric field components, transmitted and incident. Those are here. And transmittivity will be the mod of T square, which is the mod of ET over EI square, which you can say mod of ET square is nothing but the intensity of transmitted signal, or mod of EI square is nothing but the mod of incident. If I work for a normal incidence, again, like the same diagram, what will be coming out? Again, solving the Maxwell equations under normal conditions, theta is equal to 0, then I will get 4n over n plus 1 whole square over k square. Like denominator in reflection and transmission is same, right? If I add these two, right, assuming that okay, absorption is missing, then T naught, that whatever we have plus whatever R we have should be equal to 1. But at the end, we know that transmission is not ideal case. That's why we call it as a T0. As we propagate through it, absorption is taking place from incident T0. It will be like 1 minus e to the power minus alpha times the distance that it has traveled. So the first signature is T naught minus T naught e to the power minus alpha d. So the transmitted signal that is coming out will be A is equal to initiate T minus T naught minus T. So that is T is not, sorry, T is equal to T naught e to the power minus alpha d. So the actual transmission that you are getting after including the absorption in your system is given by 4n over n plus 1 whole square k square e to the power minus alpha d. So this problem is also easy. So alpha you can measure as a function of lambda, you can compute k. So now you have this, so you can work with transmission signal as well to compute the n as a function of lambda as well, right? Those are the properties of material which can give you all the information about optical properties. So up to this particular point, let me give a pass that whatever tools we require to handle our transmission data or our reflection data or our absorption data is available to us. Now, if you have any question, then please let me know. Yes. Any one of you, that if you feel uncomfortable at particular point, then please let me know. Hello? So I again will stop for a pause for a minute, and if you have any question, otherwise we will move forward.
Sorry?
So I said if anyone has any doubt, any concern, then please let them feel free to ask. Otherwise we can move forward. Right.
Please, if anyone have a question, please ask. Or you may write your question to the
Chat
message box.
box, right, text box.
Yeah, please.
Sir, on the transformation of absorption to reflection spectroscopy, because one is DRS and another one is absorption spectroscopy. So, is there any difference on the determination of band gap or any kind of thing, optical?
Okay, I haven't come to that particular point, and also I have not included it here. But
Okay.
again, to answer your question, right? So, you see, direct absorption measurement from your sample is like a means including all the signals, right? So it's more accurate result. Whereas when we come to the DRS part, in that case, if your sample is like rough, like powder samples, then perfect reflection is not possible, perfect transmission is not possible. So in that case, a lot of diffused signals will be coming because of the scattering. Those are inelastic scatterings happening in your system. So take into account then the DRS mode is preferred. Whenever we have a powder sample, non-specular sample, means you don't have shiny samples like films. We don't. So in that case, we will prefer to go for DRS mode because that is based on collection of scattered reflected signals. That's why we call it as a diffused reflection spectroscopy. And in that case, if you see the modern, because it works under a uh, uniform spherical detection mode, signal detection mode, capturing mode. So in that case, if you see, if I put my sample and if it has a reflected signal, then the diffused signal is a small component. So maximum things are reflected, so large reflection will be coming. So in that case, diffused part is small. So then data will be again spurious, and probably we will not see the right transitions that we are intending. So thin film, shiny samples which are more shiny on the surface are not advised to do with. If I have a powder sample, you don't need to worry because it is a source of diffuse reflectance. Scatterings are huge, and then you will get a reflected signal after a scattering that has a much lower intensity. In that case, it is advisable to work with. But nowadays, if you see the modern UV visible Perkin-Elmer spectrophotometer, so they have given you an option even in diffuse reflectance to work under specular conditions. So they change the detector's positions in such a way that if your sample has a relatively thin film, kind of shiny nature, where reflection is more, specular reflection possibilities are there. In that case, you can select the right detection mode by opting for DRS plus specular mode. In that case, you will avoid, because of the detector's incident signal detection conditions, they will block those signatures, specular things, and they will collect only the diffuse part. That is there. And if you collect the diffuse part, then directly again it is not possible to determine. Like in this case, we are not measuring absorbance. So we need to use the Kubelka model again to compute the first absorption coefficient alpha.
Yes.
But they are using that particular coefficient to determine the N and K is not possible because we are not working under normal conditions. So far we have discussed is good for specular samples which are good and we can work with them under normal conditions. So all these approximations that whatever we have used, t is equal to 4n over n plus 1 whole square over plus k square times e to the power minus alpha d, or r is equal to n minus 1 whole square plus k square over n plus 1 whole square plus k square. These are all for a normal condition, when my incident beam is normal to the surface. That is there. And in case of diffuse reflectance, nothing is normal, right? Everything is, that's why you use integrating sphere to collect the sample, because your signals coming out, they are reflected, scattered in all the possible directions on 360 degrees, right? So in that case, using these expressions are not advisable, and means you cannot use them because of the incident conditions are not satisfied in case of diffuse reflectance. I cannot use the diffuse reflectance data to compute the N and K. That is there.
Okay.
So that is the restriction. That
Okay. Sir, one more question.
yes.
That is very basic. I don't think so. Actually, I want to know about the difference between absorption, absorbance, and absorptivity.
Okay, write down. I will suggest you write absorption, right?
Absorbance
Absorbance.
and absorptivity, just like this transmittivity.
Okay, okay, okay. Absorption, absorbance,
Yes,
okay,
because
and absorptivity.
yes, because somewhere people are mentioning absorptivity, absorbance, absorption coefficient like that.
Okay, okay, okay. You write down three words and then I will come one by one.
Okay.
Right. Let us first take absorption. Right.
Yes.
Absorption means at a particular wavelength. Right. Absorption at wavelength lambda. Right.
Okay.
So absorption means what is the absorption at particular wavelength? Because absorption is like something defined with respect to one particular wavelength. When I say to absorptance, that includes the variation alpha as a function of lambda. So in that case, you are plotting absorptance, right? Okay, how the alpha is changing with respect to lambda. When I come to absorptivity, it is an integrated quantity. When I say integrated quantity, then alpha, even though it is a function of lambda, then I define over a defined wavelength. For example, I define absorptivity over wavelength visible light lambda is equal to 400 nanometer to 800 nanometer. Then in that case, alpha is defined, still alpha absorptivity is a function of lambda, but alpha is defined as integration of lambda 1 to lambda 2. Whatever I have got corresponding alpha lambda means like absorptance, d lambda normalized with respect to the black body radiation. Integral of lambda 1 to lambda t corresponding black body radiation d lambda, that is there, right? So the first term is absorptivity is an integrated number over the entire wavelength range, that is the absorptivity. Absorptance is a number that reflects the spectrum, that okay, how with each wavelength that is changing. So I can use absorptance to compute the absorptivity. Absorptivity is like one number, average number normalized with respect to the black body radiation. That is there.
Okay.
Right. Okay.
Thank you, sir.
Okay. So if any other question from the audience side. Okay, so no more question, then let us look back to the more practical applications, whatever discussed so far. So we have now basically all the tools. What tools are required? So now you know that after interaction of light, a portion will be getting reflected. To make my life easier, like I used only normal conditions, because if I deviate from normal conditions, these expressions doesn't look nice. You will have sine theta, cosine theta, and much ugly relations will be coming into picture. Right? Working with them is easy, not difficult, but not as easy as with the normal instruments. And if you see the practical instruments, those also carry the same information. Like if you see routine normal UV visual spectroscopy systems, there we work with the normal incidence conditions as well, except the diffuse reflectance that Peng has mentioned here. That is.
Yes.
Okay. Now looking into this, like I said, I want to probe the properties of my material. So very simple. So we discussed so far background of transmission, absorption, and reflection of light. We need to understand how measuring these quantities. Transmission you measure, absorption you measure, reflection you measure at different wavelengths, means like as a function of energy, will give you information about your materials under investigation. What is happening always, these transitions will lead to electronic transitions, and these electronic transitions will govern decide the material's properties. So these, suppose if in general we take into account of interaction of light into matter with matter, what will happen? 4 possibilities that I can list out. There may be many more, but in general 4. In this circumstances that what we are talking about, we can have interatomic transitions, like transition between the electronic levels of same atom, right? If you have more than one atom, then what may happen? That transition from one atomic side, one atomic orbital to the another atomic orbital, that we call as a charge transfer. Here, charge is transferring from atom A to atom B, that we call as a process P. Another thing is called intraband, means within the same material, your electron can transform from localized. These inner orbitals are localized to delocalized orbitals. Delocalized orbitals are valence bands and conduction bands. So this is like a process C. And another process that can happen is the transition from valence band to the conduction band. It is like delocalized state to delocalized state that we call as a band transition from valence band to the conduction band. And I'm sure all of you are aware of what are the bands. Right? That is that. We look all these four transitions with respect to different materials, and that is our interest. Okay, very simple. The first process that we call atomic transition. All of you are aware of a hydrogen atom. We can apply the same rule. So hydrogen atom atomic transitions are defined as En is equal to minus R Rydberg constant 13.6 electron volt or n square. If I take the energy transfer between two states, final minus initial, then I need to divide by E is equal to h nu, so by h. So R over h 1 over nf square minus 1 I square. So this is like atomic transitions will be governed by this simple rule. Definitely we need to use the selection rules as well, but in general, assuming that these simple transitions are involved, so these are again depends upon how the energy levels of individual atomic orbitals are displaced with respect to the ground state, and that will decide the respective energy. That is now electronic states in atoms are characterized by 4 quantum numbers that you know. Main principal quantum number that you have n. With respect to this given n is equal to 1, 2, 3, we have 4 like S, P, D, which are like corresponding to different angular momentum. Quantum number L, you will get S, P, D, and so on. And then another quantum number that justifies, that is magnetic quantum number that we call as spin. So we have N, L, M, and S. So N is the principal quantum number, L is the angular momentum quantum number that turns out to be SPDF, and then magnetic quantum number M, and then spin quantum number S. Right? So this, then, like I said, this is a simple transition that we worked out for hydrogen atom. But in general, here also within these states, these are allowed. But between these transition between N, I discussed this transition is between N, between N here, but between N also there may be possibility. But in between N, those can classify in terms of angular momentums like other vibrational states and rotational states. In that case, my transition rules, selection rules should be satisfied, like delta L means angular momentum change should be either +1 or -1. The change in the magnetic quantum number delta M should be 0 or +1 or -1. If these satisfies, then these internal atomic transitions are also allowed. Right? So, and these rules are coming again from the conservation of angular momentum, that if you impose them, because that we cannot say that is going to be true. So these are restricted with this delta L is equal to +1 and -1. So atomic transitions are easier to visualize, and atomic spectra, all of you have seen hydrogen atom, but individual atoms are not the case of electronic transitions, right? Those are atomic transitions, like differentiated by their energy difference. Now, second interesting transition is charge transfer. When you have a system made up of more than one atom, then, like I said, the transition can happen from one atomic orbital to the another atomic orbital. Very simple. Like you can say, if I have a system made up of A plus B, if I shine the light, this electron will get from A and B will capture it. So A will become plus and B will become minus. So this will be like a charge transfer. This kind of processes we call charge transfer, mostly responsible for color that we see in our gemstones. And for that, people use chromium, titanium, and iron as dopants in the sapphire or some other system as well. So charge transfer is what gives you many gemstones their color. Often impurities such as chromium, titanium, or iron are involved in the charge transfer process. Right? Chromium is the one that is involved in, many of you might be using sapphire, right? That called ruby. So ruby that you see the color, that is coming because of the chromium transitions from Al2O3, means aluminum to chromium transitions, or chromium intrinsic transitions that leads to the color after visible light interaction on your sample as well. Second is delocalized transitions, very important for very interesting phenomena. This is like here, I have put the diagram because this is like from atom which are localized electrons, like SPDF, like innermost electrons are localized electrons, topmost electrons are delocalized electrons. Those forms the band. So from localized electrons to delocalized band, when the transition is happening, that we call localized to delocalized transitions. These transitions are very responsible for photoconductivity, enhanced photoconductivity, resistivity in certain materials. For example, if I take, for example, a gallium arsenide, I shine the light, white light, its conductivity will change, and conductivity is changing because of the localized electron transition from inner orbitals to the valence band. So these are like very important. Sometimes we call persistent photoconductivity. For example, if I take indium oxide, gallium oxide, or even gallium arsenide, indium antimonide, these are the materials where you shine the light, especially little higher energy like UV light, then they excite these electrons from atomic orbitals, innermost ones, to the valence band, and then they increase the conductivity, which is persistent over a period of time, maybe minutes, maybe hours, maybe days. That is there. And that has increased, so you can use for different applications. So this is like one of the phenomena responsible for these kind of features present in your sample. Another is very common that decides the properties is like interband. This is like a transition from delocalized electron valence state to delocalized electron conduction band state. Right, that is there. So the valence band is occupied by electrons in the ground state and conduction band is unoccupied in the ground state. Right, means in general, separation between them, we call this as a band gap, right? That is used to quantify the material, whether it is a metal, whether it is a semiconductor, whether it is an insulator. So if I know the value of this band gap, then I can use it to identify. So materials with a non-zero band gap and with no free energy states available in the valence band are called insulators. Interesting, right? Materials with a zero band gap, you can call them as a metal. Materials with free energy states available in their valence states are called metals. They are not insulators. So, for example, you might have seen the definition of metals, which I would like to change from today for all of you. Right? You have seen that, okay, metals are where we don't see the bands. Right? Metals are where we see that, okay, conduction band, there is no gap. Right? Metals have band gap, and we will see that how the band gap is there. But why then they conduct electricity? We will see that is there. Right? So I need to all of you, I need for all of you to change the perception of definition that you have read so far for metal to today look the metal in a different perspective. That metal also has a gap, but the topmost band, which shows some unique features in terms of free energy states available in the valence band, made it metal, not insulator. In case of semiconductors, we have filled valence band. There no free states are available, so we call it as an insulator, right? With a small band gap. Metals have a partially filled valence band, or overlapping valence and conduction bands. That is it. So it means metals have bands. Metals have also separation between their 1s, 2s, 2p, 2p, and so on. They come up to top band. If top band is very unique, the top band is partially filled, like that we will see. Okay, we have here. So that we will put more emphasis on it, right? So bands are formed because of discrete energy levels are shifted by interaction in a solid. So 1s has a different energy separation between different atoms, and then when you join them, they will form a 1s band that is split in energy with a sum delta, right? Then why we need after 1s, why we need 2s? Because you know that all these electrons we cannot populate into one because of the Fermi-Dirac statistics and Pauli exclusion principle, right? So once 1s has been populated, we need to look for 2s, 2p, 3s, 3p, 3d, and so on. Right? So we need to fill these energy states, and we continue this. So there will be always energy gap between 1s and 2s. That is a band gap. There is a gap between 2s and 2p. That's a band gap, right? But these are inner atomic orbitals. So we don't call this as a gap, band gap. We call this as the energy gap. But the topmost filled band, that is, for example, 4s, and the topmost unfilled band, that is 4p, then there is a gap between 4s and 4p. then that gap is a band gap that we come to know, right? That gap is present in all the materials. Doesn't matter whether it is a metal, whether it is insulator. But in case of metals, that 4s band that we went up to, right, that is not completely filled. So I have empty states available in my 4s bands, and that is more important for us to see that empty states are available, so electrons can move in those empty states and electrical conduction is possible, right? So that is now how we should look for metals. Fine. So n atoms interact with n identical discrete energy states will form a band. That is fine. The continuous band distribution. Different atomic levels will form different bands like 1s, 2s, and 2p. The width of the bands will depend upon the amount of overlap. The core levels have a little overlap, so their energy separation is narrow. Whereas as we move higher in energy levels, their energy overlap is more, then they will have a broader bands. Like these bands are filled with the delocalized electrons, starting from the lowest possible energy. The energy level up to which the bands are filled, or Fermi energy, is in case of metal, not in case of semiconductors. The word Fermi level is not applicable in case of insulators and semiconductors. We use it as a misnomer that is there, right? We replace it for our convenience in a more appropriate word is chemical potential that is there. Right. Now, whatever I said to you is here graphically represented. That I said that it has metal has a gap. Metal has a conduction band, metal has a valence band, but there is something unique that my valence band is partially filled. So empty energy states are available for electrons to roam around. That's why it will conduct electricity. Right? Whether I take a sodium, whether I take a silver, whether I take a gold, right? They all have 4s, 5s, 1 electron. Right? Their 5s2 is not there. So the topmost filled band is partially filled. So if I have n gold atoms or n silver atoms, I have n silver atoms, it is 4s1, for example, not 4s2. So, right? I have n silver atom, so ns bands will come together. They will form a band. So ns bands, how many electrons they can take? They can take 2n electrons. But how many electrons are available to the 4s band? Only half of them. So half of the energy states are available. So half of the energy state, the top filled valence band of silver are available to conduct the electricity. And the band gap exists, and then you have a conduction band where no energy states are filled. Now that is there, right? So this is the reason that why metal is conducting electricity, even though it has a band gap, right? So this is one thing that is different rather than band gap. Metal doesn't have a band gap is a wrong statement, at least in my understanding. And I believe I have tried to convey the reason why this is there, right? Another case of interesting metal is there. When you have a conduction band, because of the strong overlap between their orbitals, conduction band comes down to the valence band. In that case, your valence band is completely filled, but because of this overlap, and now the relative shift of conduction band below the valence band, your empty states are available. Your conduction band electrons will move from valence band to the conduction band made under equilibrium. Then these free states are available here as well as here as well. Right? So in that case, free energy states are available. In this case, the gap, which we define as the difference between the conduction band to the valence band. In metal, this band gap is positive. Whereas in this case of metals, where band gap became negative because EC minus EV, EC is lower than EV, so it became negative. These kind of metals are very unique and we call them semi-metals. Example is tin, tellurium, mercury telluride. These are the materials where band gap is negative. What does it mean? Your conduction band has shifted below. Then another situation is there, okay, they are touching each other. That is a different story. So that is there. So now we see, so here band gap existed, band gap is available. In one case it became negative, in one case it may be zero, in one case it is not zero, but still metal will conduct electricity because of the partially filled top band. Right? Half of the energy states are available in case of silver, gold, sodium, potassium, whatever metal you take, and copper, anything. And because of that, electricity is conducted as well. Now take the interaction of light with metal, how this will be interacting. So incident light is coming and falling on the materials. What will happen to that? They will interact with this And then depending upon the incident frequency, we define the dielectric constant for my metal. 1 minus omega p square omega square. I am taking the liberty that all of you might be interested in how, from where I am getting. Very simple. Again, solving the difference, solving the Maxwell equations, interaction with matter. Then I will get, and this has been solved in optical properties of solids by Kittel, right? In Kittel's solid state physics book, that optical properties of materials chapter, right? So this is the dielectric constant. So you see, I have a unique frequency that is given by Ne square or epsilon naught m. Well, this is called as a Plasmon frequency, collective electron oscillation frequency that depends upon the number density, and rest is constant. So if I assume that this is there, and then I take omega is less than omega p, then my epsilon will be less than 0. Then my refractive index will become imaginary, Ik, and then the light is attenuated because of this n, this is extinction coefficient, and does not propagate. In that case, t will be 0 and reflection will be 1. When omega is greater than omega p, then epsilon becomes positive, right? Then in that case, the wave will be propagating forward direction. Then I will have r that is less than 0 and t will be greater than 0. What about omega is equal to omega p? Epsilon becomes 0, right? So what we will get? We will get epsilon is 0, and when epsilon is 0, n is 0, right? In that case, you will see the complete wave is getting absorbed because the incident wave will be in the resonance of collective oscillation of electrons that we call as a Plasmon. And that's where you see why all metals are reflectors. This is the reason that whenever the light, incident light, has a frequency smaller than the frequency of plasmons in your system, light is getting reflected. Even in visible also it is reflected, right? Now it will start absorbing as we move closer to the plasmon frequency. Higher the plasmon frequency, more in the UV region, and then you will see a small signal that is getting absorbed. So this is the reason why metals are all reflectors. So if you simply measure the reflectance from your material, and then if you find that okay, this is the nature, that okay, you can find out whether this is a metallic or non-metallic as well. Then semiconductors, like I said, you have a band gap, you have respective thermal energy or chemical potential, right? In that case, I can use the incident light again to interact with my material. Since your valence band is completely filled, so if my incident energy is smaller than the band gap energy, the material will not see those energy photons and they will pass through it. So for example, I will give you an example. If I take a silicon, right, in place of silver, I take a silicon, and if I allow the light to pass through, that is a visible light, in that case, what will happen? The incident light which you are allowing to pass through on a silicon whose energy is less than the band gap energy will pass through. That's why silicon is transparent to infrared light. Can pass through your material which looks opaque from your eyes when you visualize it, right? That is that. But as soon as the light comes near to the 1 electron volt approximately, you will see that light starts getting interaction starts, and photons energies are absorbed, taken by electrons to move them from valence band to the convection band. And this phenomena we can use it to again find out the nature of band gap as well as the numeric values of these band gaps. Additionally, if I have dopants, then my respective bands will Fermi energies will shift, and depending upon the level and depending upon their energy distribution, we can also try to find out these distributions in the sample using this simple spectroscopy as well. Now, I said we will use it to find out the nature of band gap, whether it is a direct band gap or an indirect band gap, like we define the simple spectroscopy, right? And we can get measure alpha from this simple experiment, but we see that energy band diagram, and if it is a direct band gap, then it is a K is equal to 0 process. There is no momentum transfer is involved. Directly energy is taken from the valence band electron and shifting them to the conduction band electron. Right. In that case, the valence band maxima and conduction band minima are at the same point. Right. So that we can take into account. In that case, very simply we can see that no phonon is involved to satisfy the need of momentum conservation. Whereas if I have an indirect band gap, where they are not at the same key point, in that case, direct transition cannot happen. So band gap is still small, but to take the band gap into account and satisfy the conservation laws of momentum as well with respect to with the energy as well, we need to take into account the absorption or emission of respective lattice phonons. Right. So again, like taking into account measuring alpha as a function of energy, if I plot alpha square versus E, and if I see a direct sharp transition in my alpha with respect to the zero portion, then I extrapolate that particular region to extract the band gap of my value. And if this sharp straight region comes in alpha square versus E, then it is a direct band gap. However, here no phonon transitions are involved. However, if I have an indirect band gap, then in that case, phonon emission is involved or phonon absorption is involved. That is like a lattice vibration. If my phonon emission is involved, then energy will be alpha will be defined as h nu minus band gap energy minus E phonon whole square divided by the sum factor. And then when absorption is involved, then Eg plus EPH will be there. H nu is the incident energy. So in that case, if I take the square root of alpha, then this will become my incident energy E minus Eg minus EPH, or square root of alpha is E minus Eg plus EPH. This rest is constant that we, for the time being, we can ignore. Then now I plot square root of alpha versus energy, like here, square root of alpha versus energy, I will get two processes. One is respecting to phonon absorption, one is with respect to the phonon emission. And I extrapolate both the bands together. I extrapolate them to the zero process. What I will get Eg minus EPH and Eg plus EPH, right? So I average these two numbers and divide it by 2, I will get the band gap of my material by excluding the contribution of phonon. That is there, right? So whenever your material is a direct band gap, much easier to work it out. Whenever in that case, because you are not worried about this expression will be A times H nu minus Eg whole square, right? This expression has no meaning in that case, right? But whenever my band gap is indirect, in that case I need to be more careful. If you want to put a numeric value of your band gap, then you need to take care of both the phonon emission and absorption processes, and then you extrapolate and then you average them out to get the real band gap of your indirect band gap of your material. Okay, then various applications of these properties are there. You can design the materials with different absorption windows, different transparent windows. I'm just giving you as an example. Like here you have a crystalline insulator and semiconductor. This is like an insulator sapphire. If you see it is transmission is 100% or near to 100% in the visible region. Whereas if I take a CDS, that is also here you see a complete visible light is getting absorbed, and here transmission region is different. What is the advantage? Here advantage is that by selecting the material with a suitable band gap, because band gap tail is determined by from this transmission tail. So by selecting the different material with a different band gap or different optical properties, you can design the optical filters, right? This is an optical filter in this window. This is an optical in this window. So you block, suppose you don't want to pass the visible light and you want to pass the lower energy light, you can select that respective band gap material, and then a respective band filter can be, optical band filters can be designed as well. Similarly, I said in the beginning, like, okay, like pure sapphire is transparent to the entire wavelength range from UV to the lower wavelength side as well, right? Higher wavelength side as well, means lower energy. When you put chromium inside it, and if you see this is a ruby crystal, when you put chromium, then you see different transitions are coming. These are like charge transfer regions, like the process B that I have used, that can give you, depending upon the doping and transition regions, then they can give you yellow green region, blue band region, or even red band region as well. That is there, right? So you can define. So in this case, if you see absorption is starting in this region, like in optical region. Whereas in this case, in sapphire, pure sapphire system, there is no optical absorption. So that is there. Similarly, you can design other optical materials by manipulating the refractive index and their constants as well. So another interesting experiment is there that you can do a simple thin film UV visible spectroscopy experiment to determine the thickness of the film. That right, very simple. I take incident light getting reflected from the top surface, getting reflected from bottom surface. I can compute path difference, that is d, which should be equal to n lambda. Right, and then since you know that this is not a unique lambda, so in that case I will have n lambda 1 and lambda 2 parts. So I work it out, solve the diffraction conditions. Delta L is equal to 2 times d times n, which is equal to m lambda. If I solve this particular equation, then I rearrange and solve this. D is equal to 1 over 2n lambda 1 into lambda 2 over lambda 1 minus lambda 2. This experiment that you can do in your lab. And then you can see the transmission fringes which are coming. Then you can compute lambda 1, lambda 2, lambda 3, and corresponding simultaneous lambda 1 and lambda 2. These are adjacent maxima or even adjacent minima. You can backplot, and refractive index value you can take as the average value of lambda 1 and lambda 2 from the literature. You can find out what it is, and you can compare their results with the much more complicated scanning electron microscope cross-sectional images, and then you will find those are matching as well. Right, with the error of few nanometers. Additional information, suppose if you have a defects or even like additional regions in those your systems, those can be also started. So I think I am getting out of time if I am right, because I see sometimes Professor Tiwari is turning in and out. So I think rather than looking into more complicated processes, I can stop it here. Right, looking into more different processes as well. So I will stop it here, and if you have any question, then most welcome. Otherwise, I can summarize in few terms a very simple experiment.
Please summarize.
That can give you the information about optical properties of your materials by doing transmission, reflectance, and absorption experiment to find out the refractive index and extinction coefficient and the dielectric constants as a function of wavelength, number one. Second, you can quantify whether it is a metal, whether it is a semiconductor or an insulator by measuring the band gap. Then you can use them to find out the thickness of your optical thickness or thickness of your film by doing this interference experiment and measuring out the simultaneous maxima or minima and back plugging into the interference condition to get d 1 over 2n lambda 1 over lambda 2. And many other electronic processes can be found out. Like I will just give you a flavor. You can find out Hawk plot, Bachtail, and see the defect region to give many more informations about your defect related processes involved in this. You can use absorption spectroscopy like in chemistry to find out the concentration of your materials and so on. Like these are additional things, very simple. So with this, I can think I can end up and then take the questions if you have.
Thank you, sir. Thank you very much. And I request the audience, if they have a question, please ask. So I think if anyone have a question, even later on, please write your questions on a chat box, or you may mail us. We will communicate with Professor Ambesh sir, and certainly he will discuss and pose the questions. So let's thank again Professor Ambesh Dikshit sir, and it's very nice for him that he has given us his time, and he has spared time and discussed a really nice subject to us, and we are really very happy to have him. Thanks a lot, sir. Thanks, sir.
Thank you. And then I think now I can take the liberty to be out.
Sir,
Right. I will request you to leave me because of my other assignments. That will be easy for me to take care of those things as well. Right.
there is one question. Is there any technique to calculate? One question here.
Perfect
Is it-
transmission. Okay, perfect transmission with respect to, it will be always with respect to some reference. So there is no absolute transmission when you compute it experimentally, right? So suppose if you have a material based on some reference, right? So we always compute with respect to that particular reference. That is there. To get absolute transmission, it will be like very difficult to find out.
Yeah. Thank you, sir.
Yes. Okay then. Thank you to you all, and I will take the liberty to get excuse from taking me out from the conference. Otherwise, I would have enjoyed the talk from Dr. Ranjan Jha as well. Okay.
Thank you, sir. And
Okay,
we will have some discussion some later time on
Sure.
on a detailed one. We'll see.
Okay.
Thank you, sir. Thank you
Thank
again.
you.
Thanks.
Thank you, sir.
So, welcome, Dr. Rajan, sir. Good morning.
Good morning. Good morning. Good morning.
How are you, sir?
I'm fine. Thank you. How about you?
It's really very nice to see you.
Same here. Same here.
Yeah, it's very after a long time.
Yeah. So how are things going?
Yeah, everything is fine. Everything is fine.
Okay.
So I think we can start within 5 minutes.
No problem. No problem. Please let me know. I'm ready.
Yeah, thank you.